Problems involving two triangles on page 26 or 7 are definitely A type questions. So be prepared to be thinking a little bit outside the square, but using the basic rules that you've learnt with Pythagoras and trigonometry and bearings to assist you. You need to draw a large clear diagram. Always check that the diagram fits the question once you've drawn it, and then try and make a strategy for solving the problem. You should be able to devise a method that will see you to the problem's completion before the maths work is started. So, you might have two unknowns. How are you going to solve one of those to then assist you further in the question? So let's have a look at a couple of different questions so that you can see an idea of how these go. So we've got a woman standing at position A, finds that the angle of elevation to the top of a 220 metre high tower is 37 degrees. Upon walking to position B, which is closer to the tower, she finds that the angle has become 59 degrees. Find the distance that the woman walked in between making the observation. So what do we know? We know there is a 220 metre tower. We know that she is standing away from the tower at 37 degrees looking up to the top of the tower. And that was position A. Upon walking to position B, which is closer to the tower, she finds that the angle has become 59. And you'd expect that. As you get closer to something, the angle gets higher. Find the distance that the woman walked in between making the observations. So we're trying to find x, the distance between here. But you can see that that is not a right angle. This is here, this first triangle looking up from B is, and if you look up from A, you can see that's a right angled triangle, but this triangle itself is not. So you just need to be mindful that you need to be working with the right angles to try and find unknown sides. So I'm thinking about, I've drawn my diagram, I've just had a quick read through and it matches with the information that I've got up here. I might label some other sides. I think I'm going to need to know this side. So what will my strategy be? I know that I can work out side Y. I think I need to work out what, call that Z, the total distance is here, because if I know this distance, and if I take away this distance, I'll be able to work out what x actually is. So that's going to be my strategy. So let's work out Z first, which is this long one here. So you might choose to redraw that portion if you find that the whole diagram is a little bit complicated. So it might look something like this. So we're using the whole triangle is 37. We know that's 220. And so we're trying to find that total distance. So that simplifies the diagram. So opposite and adjacent. So we're going to use tan. So tan of 37 equals 220 over z. Doing our little trick where we swap those. Z is equal to 220 divided by tan 37. And so the distance for Z equals 291.9 metres. So we know this distance here now. Let's find distance Y. So you might wish to draw another little triangle. So that's 220 as well. And because we've now moved in, it's 59 degrees. So it's going to be the same formula because it's using the same sides that we were before. So tan of 59 equals opposite, which is 220, over side y, and then swapping those two around, y equals 220 over tan 59, and so y equals, if you solve that, 132.19 metres. So now we have the total distance, which is 291.9 metres. We have distance y, which is 132.19, and if we take 291 and we take away 132, we'll be able to get distance x, which is our unknown distance travelling from A to B. So what are those numbers? 291.9 minus 132.19 will give us a distance of 159.76 metres. So that's the first example where you've got two triangles. Always look for smaller triangles within the larger one to help you out. Our last example that we've got is a vector style problem. So we've got a ship leaving a port and it's sailing due north for a distance of 5.5 kilometres before turning and sailing a further 6.2 kilometres on a bearing of north 28 degrees west. Find the distance and bearing of the ship from its port. So let's draw the diagram first and then check our diagram to see if it fits with the information that we've got. So a ship leaves port and sails due north. So as soon as I see information like this, I think I'm going to draw myself a north, south, east and west diagram for a distance of 5.5 kilometres. Let me just draw that down a little bit more on the page because I can see that I'm going to be heading up and then across. So if I start down here, due north, 5.5 kilometres, before turning and sailing a further 6.2 kilometres on a bearing of north 28 degrees west. So I'm drawing myself another little north, south, east, west. Find the distance and bearing of the ship from its port. So we need to find the distance from here to here, but we also need to find the bearing of the ship from the port, so from the start. So if we were here, looking back, what would this angle be? And it would be north so many degrees west. So there's two things that we need to do. So if we have a look at this, there's no right angled triangles here at this point. So what we need to do is put some in so that can assist us to find some of the sides. So if we extend this one across and down, we've got a small triangle here, okay, and then we've got a larger triangle here and here. So the information that we have is we can use this angle and this distance to find this side. Let's call it side Y, because what we're trying to do is try and find this length. So to find that length we need this distance and we need this distance, but we haven't got that information yet. What else do we need to find out to help us? We need to find this distance here. So again, we can use this angle and this distance, and let's call that side X. And so then we can use that to find the total distance here. We'll have distance y, and then using Pythagoras, we can find our hypotenuse. So let's label this triangle 1 and this triangle 2. Let's pull out triangle 1. And redraw that so it looks a little bit more simple. So we're trying to find y and x, and we know the angle here is 28, and we know this distance is 6.2 kilometres. So let's find x first. So x, here's the angle, it's adjacent to it, and here's our hypotenuse. So let's use cos. So our angle is 28. Adjacent is what we're trying to find, and our hypotenuse is 6.2. So 6.2 times cos 28 equals side x. And so x equals 5.47 kilometres. Let's try and find y now. We could do y two ways. We could use Pythagoras, or we could use one of our trig rules. Let's use another trig rule. So if we have a look here, we've got y is opposite the angle, and let's use our known 6.2 kilometres there. So let's use sine. Sine of our angle is opposite over hypotenuse, so sine 28 equals y over 6.2. So 6.2 times sine 28 equals y. And so y is going to equal 2.9 kilometres. So we've got those two sides that we were trying to find previously. So this is 2.9 kilometres, and y was 2.9 and x was 5.4. So now we've got this distance and this distance. You can see why this is an A-level question, because there's lots of parts to it. So we now need to add the 5.47 to the 5.5 to get the total distance here. So that's going to be 10.97 kilometres will give us this distance. So now we know that this is 2.9 kilometres from here to here. We know this is 10.97 kilometres. We can then work out what this distance here is using Pythagoras. So knowing our formula for a right angled triangle, for our hypotenuse is a squared, side b squared, plus side c squared is 128.75, and so the square root of our answer is 11.35 kilometres. So now we've worked out the distance from here to here. So that's the first part of the question. The second part is working out what this bearing actually is. So it's going to be north so many degrees west. So I think what we'll do is we will just redraw that diagram again so that we can work out what this little angle is, and so that it's a little bit clearer for us. And because this is a longer video, I'll have to do it in a smaller video to finish it off.